everyone! Today is the day. This integral right here took me months to solve, on and off, and today we are going to solve this integral once and for all. And the answer is really nice, so stick around for that. So, how can we evaluate this integral? Well, at first, we will introduce a substitution. We will let some u be equal to e to the x, which means du will be e to the x dx, and now if we divide both sides by e to the x, we get dx is equal to 1 over e to the x du. But what is e to the x? It is precisely u, so we get 1 over u du. And now we can just substitute everything in to get the integral from, okay, e to the 0 is 1, e to the infinity is infinity. So we have our 1 over u because of our differential dx, and the natural log of, let me do this again, the natural log of u plus 1 over u minus 1 du. And now we will use integration by part on this integral. So put down the d, the I, the plus, the minus. Okay, and now we will differentiate this weird logarithm, so natural log u plus 1 over u minus 1, and we will integrate 1 over u. Integral of 1 over u is simple, that's just natural log of u. But then for this one, let me do this in a different color, I don't know, red, like this. The differential with respect to u of natural log of u plus 1 over u minus 1, or rather the derivative, I'm sorry. So, the derivative of natural log is 1 over u, as we have already found out there. So we'll have u minus 1 over u plus 1, reciprocal of this. And some people are like really having fun outside, it seems. Times, and then use the quotient rule, we get u plus 1, derivative of u plus 1 is 1, so u minus 1 minus derivative of the bottom is 0, is 1, so we get u plus 1. And now all divided by u minus 1, whole thing squared. And now u minus 1 is going to cancel out. These two u's are going to cancel out. And we'll be left with negative 2 on the top. And in the bottom we have a difference of 2 squares. U plus 1 times u minus 1, which is simply u squared minus 1. And now we can just distribute the negative sign down in the denominator to get 2 over 1 minus u squared. So derivative of this is just 2 over 1 minus 2 squared. Not n squared, u squared, please. Like this. And now we can just do all of the usual stuff and everything. So we get natural log of u times the natural log of u plus 1 over u minus 1, evaluated at 1 and infinity, and then minus, I'll factor out the 2 times the integral from 1 to infinity of natural log of u over 1 minus u squared du. And now, what happens if we plug in infinity into here? Well, natural log of infinity is infinity. And then for the argument of this second logarithm, as u goes to infinity, u plus 1 over u minus 1 goes to 1. You can easily verify that using L'Hopital's rule. Natural log of 1 is 0, so we get an infinity times 0 situation, which means evaluating this will be a job for limits. So we will have the limit as u goes to infinity of natural log of u times the natural log of u plus 1 over u minus 1. And now, as we said earlier, this is an infinity times 0 situation. So to evaluate this limit, we will observe that natural log of u is simply 1 over natural log of u. So we'll have the limit as u goes to infinity of natural log of u plus 1 over u minus 1 over 1 over the natural log of u. And then this thing right here goes to 0, as we said earlier. Natural log of u goes to infinity as u goes to infinity. 1 over infinity is just 0, so we get a 0 over 0 situation, which means we can use L'Hopital's rule. So we'll get the limit u goes to infinity. Derivative of this, we have already evaluated this right there. This is just 2 over 1 minus u squared all over. So we get minus 1 over natural log squared of u, because the derivative of 1 over x dx, using the chain rule and everything, times 1 over u, because as I said earlier, of the chain rule. And now just factor out the 2, so we get 2 times the limit as u goes to infinity of, 1 over u natural log squared of u is just u natural log squared of u. So we'll have that in the numerator, and in the denominator we can distribute the negative sign to get u squared minus 1. And now let's see. As u goes to infinity, u goes to infinity. That is pretty trivial. Natural log squared of u goes to infinity. U squared minus 1 goes to infinity. So we have infinity over infinity situation, which means we can again use L'Hopital's rule. So we get 2 times the limit as u goes to infinity of, use the product rule on the top, natural log squared of u plus 2u natural log of u, because of the power rule, times 1 over u. But the u's will cancel out, so we'll have 2 natural log of u. Derivative of the bottom is just 2u. The 2's cancel out, leaving us with this limit right there. And the dog just barked. I got pretty surprised, right? Oh, okay. Stop barking, dog, please. Okay, so natural log squared of u goes to infinity. 2 natural log of u goes to infinity. Infinity cos infinity is infinity. As u goes to infinity, u goes to infinity, so we have infinity over infinity, which means we can use L'Hopital's rule yet again. So limit as u goes to infinity of 2 natural log of u over u plus 2 over u. All of this divided by derivative of the bottom is just 1, so we don't need to care about that, because dividing by 1 is the same thing as doing nothing. And now, as u goes to infinity, 2 over u goes to 0. So we are just left with a factor of the 2, so 2 times the limit as u goes to infinity of natural log of u over u. And now, natural log of u goes to infinity as u goes to infinity. Same thing for u, so we get infinity over infinity, which means we can yet again use L'Hopital's rule. So we get the limit as u goes to infinity of, derivative of natural log of u is 1 over u, and then derivative of the bottom is just 1, so we don't need to care about this. And then as u goes to infinity, 1 over u goes to 0, so we get 0 times 2, 0 times anything is 0, so we get this goes to 0. Therefore, at infinity, this thing will go to 0. But then what about if we plug in 1? Natural log of 1 is 0, and then for u plus 1 over u minus 1. Keep in mind that this is technically 1 plus, since we are approaching 1 from the positive branch. So since we're approaching 1 from the positive branch, u plus 1 over u minus 1 goes to positive infinity. Natural log of infinity is infinity, so again we have a 0 times infinity situation, which means this will be again a job for limits. So let me do this in another color. So we'll have, and we see the limit as u approaches 1 from the positive branch of the natural log of u times the natural log of u plus 1 over u minus 1. And then we can use the same rewriting trick that we did right there to get the limit as u approaches 1 from the positive branch of natural log of u plus 1 over u minus 1 over 1 over the natural log of u. Because at the top we get infinity, at the bottom we get 1 over 0, which is infinity or negative infinity, depending on which side you approach it. But as you go from 1 to the positive range, this will be infinity. But either way, we will have an infinity over infinity situation, which means we can use L'Hopital's rule. So I will skip all of the steps of differentiating because we essentially get this same thing right there, because these are the same expression that we take limits, and as I said, there are some people really having fun outside. So we get, so as I said, we'll skip all of those steps and go directly here. So we get the limit 2 times the limit as u goes from 1 from the positive branch of u natural log squared of u over u squared minus 1. And now I would like to split this thing into 2 limits. So we'll group natural log squared of u and u squared minus 1 into one limit, and we'll multiply that by the limit as u approaches 1 from the positive branch of u. That was our u that was right there just before. And now this right here is just 1. Nothing too scary there. And for this limit, natural log of 1 is 0, 0 squared is 0, 1 squared minus 1 is 0, so we have 0 over 0, which means we can use L'Hopital's rule. So we have 2 limit u goes to 1 from the positive branch. So on the top we'll get 2 natural log of u times 1 over u. In the bottom we will get 2u. These 2's right here cancel out like this, and we're left with our 2 times the limit as u goes to 1 from the positive branch of natural log of u over 1 over u times 1 over u is just 1 over u squared. And now natural log of 1 is 0. 1 squared is 1, so we get 0 over 1, which is 0. So this limit goes to 0. 0 times anything is 0. So we get 0 right there and 0 right there. So this whole integral simplifies down to -2 integral from 1 to infinity of natural log of u over 1 minus u squared du. I barely had the space to write everything. And now I'll clean up all of this board to make more space, and we will continue evaluating this integral. Okay, so now that I've cleaned up this board, we can finally start continuing to evaluate this integral. And here's what we want to do for, well, here is our next step. So we will consider the power series expansion of 1 over 1 minus x. This is just the sum as n goes from 0 to infinity of x to the n, because it's just a geometric series with first term 1 and common ratio x, so use the geometric series formula or something. So what happens if we plug in u squared into this? So we get 1 over 1 minus u squared equals the sum as n goes from 0 to infinity of u to the 2n du. So we want to substitute this infinite series into our integral in some way. But we can't do that yet, because this series converges on the open interval from -1 to 1. You can use the ratio test, the root test, I don't know, the geometric series to verify that. But as I said, this converges from -1 to 1 exclusively, and we're integrating from 1 to infinity. So we can't plug this series into our integral, but what we can do is introduce a substitution. And our substitution will be that we'll let t be 1 over u. So this means that u will be 1 over t, you can multiply by u divided by t, and taking the differential on both sides, we get du equals -1 over t squared dt. And now we can just substitute everything in. So we get -2 integral from, okay, 1 over 1 is just 1, 1 over infinity is 0, and then we get, let me see, natural log of 1 over t over 1 minus 1 over t squared times -1 over t squared dt. And now we can use this negative sign to switch the order of integration. So we get the integral from 0 to 1. And then natural log of 1 over t is just, let me do this in green. Natural log of 1 over t is natural log of t to the negative 1. So this right here is negative natural log of t. These two negative signs will cancel each other out. So we will get 2 times the integral, that was an ugly integral sign, times the integral from 0 to 1 of natural log of t over t squared minus 1 dt. But then we can just put a minus sign on front to switch the t squared and the 1 to get 1 minus t squared. And now we are in the interval of convergence of this infinite series, well, except for the one where it's an improper interval anyway, so we can still plug this series in. So we get negative 2 times the integral from 0 to 1 of, and then I'll just bring everything into the infinite series, sum as n goes from 0 to infinity of t to the 2n, I just farted, natural log of t dt. Again, we brought the natural log of t inside the infinite series. And now, what we want to do is we want to interchange the infinite series and then the integral. And we can do so if the infinite series absolutely converges over the interval for which we are integrating. And we don't need to worry about the natural log of t since it's a constant with respect to n. And the sum as n goes from 0 to infinity of t to the 2n converges from 0 to 1, but not at 1, but from 0 to 1 it does, and this means we can just use limits, plug the 1 back in and everything, but we're not here for mathematical rigor, we're here for finding the answer. So we'll just interchange these two operators. So we'll get negative 2 times the sum as n goes from 0 to infinity of the integral from 0 to 1 of t to the 2n natural log of t dt. And now, here's what we will do. We will multiply our integrand by t and then divide it by t. So we haven't changed our integrand. And now we'll introduce a substitution. Namely, we'll let some w be the natural log of t, which means dw will be 1 over t dt. Exactly what we have here. And there's a plane going by. I am sorry for that. There are so many planes going by these days. I don't know why COVID restrictions have relaxed or something, because now planes can travel anywhere. Okay, never mind. So we get, plugging everything in, we get negative 2 infinite series from 0 to infinity, integral from, okay, natural log of 0 is negative infinity, natural log of 1 is 0, and then we get our w because of our natural log of t, and then if we take a look at this equation right here, take the exponential on both sides, we get t is equal to e to the w, so we can just substitute this in, use exponent properties to get e to the w times 2n plus 1 with respect to w. And now we will introduce yet another substitution. We will let some y be negative w times 2n plus 1. And now we'll divide both sides by negative 2n plus 1 to get w is equal to negative y over 2n plus 1. Take the differential on both sides, we get dw is equal to negative 1 over 2n plus 1 dy. And now we'll just substitute everything in. So we get negative 2 right there times the sum, and goes from 0 to infinity of, okay, so we get negative infinity, which is infinity, so lower bound is infinity, and then upper bound is just 0 because 0 times anything is 0, and then for w we have negative y over 2n plus 1 times e to the negative y times our differential dw, which is simply negative 1 over 2n plus 1. This is not a minus, this is a multiplication sign, dy. And then we can use this negative sign to interchange the two bounds of integration, so we get integral going from 0 to infinity, and then these two negative signs cancel each other out, and we can factor these two 1 over 2n plus 1 terms out of the integral, so we get 2 sum n goes from 0 to infinity of 1 over 2n plus 1 squared times the integral from 0 to infinity of y e to the negative y dy. But then y is simply y to the 2 minus 1, because this is just y to the 1, which is y. And this right here is just the gamma function evaluated at 2, and this is just 2 minus 1 factorial, which is from 1 factorial, which is 1. Therefore, this whole integral vanishes to 1, and we're only left with this infinite series to care about, namely the sum as n goes from 0 to infinity of 1 over 2n plus 1 whole thing squared. And now we can just write out a few terms of this series. So we get 2 times the sum of, let me see, so we get 1 over 1 squared plus 1 over 3 squared plus 1 over 5 squared, 1 over 7 squared, so on, so on, so on, up until infinity. And now, what we want to do is we want to add in all of the missing even terms that go in between, and then subtract them again. So we will have, so here we will have a 1 over 2 squared, 1 over 4 squared, 1 over 6 squared, 1 over 8 squared, and so on, so on, so on. So we get, let me write this, so we get 2 times, okay, so we get our entire sum, 1 over 1 squared plus 1 over 2 squared, 1 over 3 squared, all the way up until infinity, minus the sum of all of the even terms we added, so 1 over 2 squared plus 1 over 4 squared, that squared looks like a del, 4 squared plus 1 over 6 squared, all the way up until infinity. And now, 2 is 2 times 1, so 2 squared is 2 squared times 1 squared. 4 is 2 times 2, so 4 squared is 2 squared times 2 squared. 6 is 2 times 3 squared, so we'll have 2 squared times 3 squared, and this goes on for all of the terms in this second infinite series. And now we can see that we have a common factor of 1 over 2 squared, or rather 1/4, which we can easily factor out of this infinite series, so we get negative 1/4 there, and we can erase all of these 2 squared. And now, these two sums, this and this, are exactly the same, which means we can kind of factor them out. So we'll have 2 times this sum times 1 minus 1/4, or 3/4. So we get 2 times 3/4, which is 3/2, times this sum right here in parentheses. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, so on, so on, so on. But we know this sum right here, this is just equal to pi squared over 6. And then 3 over 6 is 1/2. 1/2 times 1/2 is 1/4. So we get an answer of pi squared over 4. Finally, months of misery ended today. Now I don't have to worry about this crazy integral anymore. So this is new video. So I think that watching the video, the regular lecture is on, and see you in the next video. Bye. Why isn't the end card rolling? Come on. Roll the end card. Roll the end card. I said roll the end card already.